Hi everybody. We're going to pick up some of our final bits and pieces from the lectures on higher order functions. This is section 1.2. So we'll do this a little bit and then move on to 1.3, some general discussion on expressions, values, and the notion of evaluation. So we're backing up to some slides we skipped past earlier when we moved through this material. And we just want to look at a few ways in which we can manipulate functions in a relatively nimble way in a language like OCaml. All right, so we may want to change the order in which a function takes its arguments. We may want to compose two functions, or we may want to curry or uncurry a function, right? So currying is the process of taking a function that takes arguments as a tuple and turning it into a function that takes its arguments one at a time, as we're sort of used to seeing in most of the OCaml functions we've written so far. And then to uncurry a function is to go the opposite direction. So we might consider a function like flip, right? So if we look there on the screen, you see let flip f of a of b equals f of b of a, and wonder, well, what exactly does that mean, right? So you may define this in our file flip.ml. This is in the public repository, and in our sample programs directory. And we don't need much of the slides anymore, so we'll lift this window, make this a little bigger. So, all right, we see the type of flip there, right? It takes a function that is type tick A to tick B to tick C, and just turns around those first two arguments, right? So another way we could think of defining flip is to say, well, flip is something that takes a function and it returns a function, right? And this is a function that's going to take its arguments A and B and then apply them in the reverse way, right? So maybe we'll change these names to B and A to correspond with the type variables that we see in the type signature in the UTOP session. All right, so here we can see that what we're returning is a function that takes a B and an A and then applies F to those in the reverse order. And if we load this again, we'll see that we won't load it again. Now let's load it again. All right, we get the same type as we had before, which is still just seen at the very top line of the terminal session there. All right, so what can we do with such a thing? Well, to motivate this, let's step back and recall our friend add, which is x plus y, and little helper or little functions we can write, such as increment all, which maps this to map an increment function across a list of numbers, right? And so we could say, well, let's just call add of 1 over x's, and this would do the trick for us. Right, so if we load this again, we see increment all is an int list function, so we have the list 1, 2, 3, we get back the list 2, 3, 4. And so, well, that's sort of nice. So let's think of doing something similar with subtraction. So if we have subtraction is x and y is x minus y, we may decide, well, all right, let's decrement all the elements in a list, and let's just map subtract 1 over that list of x's. And, well, we have the right type, but if we want to decrement all these values, so 11, 12, and 13, well, this isn't quite right. We get negative 10, negative 11, and negative 12, right? And the reason is that what we're really doing is subtracting all the elements in the list from 1, right? So it's 1 minus 11 gives us negative 10, 1 minus 12 gives us negative 11, and 1 minus 13 gives us negative 12. So this doesn't really do what we would like it to do. All right, we may name this decrement all incorrect to indicate this isn't quite what we're after, right? But this is where we might use our flip function, right? So we can define let dec all of x's, right, is to be list.map, where what we want to do is flip subtraction and apply it to 1 over x's. And so just to test this out, we may say, well, what is flip of sub applied to 1? All right. What is this? What is this? Well, this is an int to int function, and if we apply this to 5, right, we do in fact get 4. So the little extra new lines in there that aren't too helpful, but hopefully we see the idea here. So now if we try decrement all across the list 10, 11, and 12, right, we do in fact get 9, 10, and 11. Right? So what we did, flip is just a function that changes the order of the arguments to the function that we pass it. Right? So flip is higher order. It takes a function as input and gives us a function as output. Right, we can do similar things with function composition. Right? So thinking of a function that we'll name it compose, and it takes a function from B to C and then a function from A to B, and is going to return a function from A to C. Right? So we're going to compose these, so now our input is first flows through the second function, that output then flows through the first function to give us the output of the entire thing. So how might we define compose? All right, so again, we'll say this is something that takes a function f and a function g, and what is it going to return? Right? It's something that should return a function, so we can say, well, it's a function that takes an x, the final argument, the first argument, and applies f to the result of applying g to x. So if we load this again, all right, we see that our types are correct, except the letters are not lining up exactly with the type variable names here are different than the type variable names I chose in the slide, but otherwise they look to be the same thing. So what might we do with compose, right? We can think of letting a function to square and then increment a value x be the composition of a function that is a square function and our increment function, add 1. All right, so what does square of increment do? All right, well, it first increments something, right? 5 becomes 6, and then we square it. And so this is useful in a few places, right? So if we wanted to do something like this over a list of integers, we might define a function that we'd call increment then square all that takes a list of x's. And without using our compose function that we've created inside the utop session, right, we may say that what we want to do is map our function square. Right, so let's define square first, over the result of mapping increment, so add of 1, over the list x's. And we can see, does this do the job, right? So if we increment then square the values in 1, 2, 3, sure enough, we first increment 1 to 2, square it to get 4. We increment 2 to get 3, which squares to 9, etc. Right, but here we're making 2 passes over the list. Right? Can we do this so we make just 1 pass over the list? So we'll call this one increment then square 1 pass. And we like to have one map and then a function that is applied to x's. right? And here we could use compose, right, to say that what we want to do is to compose square with add of 1, right? And this should give us the same result. It will give us the same result. All right, so now increment, then square all gives that one. 1, 2, 3 is 4, 9, 16. Right, and in one pass we do exactly the same thing. All right. Right. Finally, we might take a quick look at functions that curry or uncurry a function. Right. So we may decide to write a function called curry that should take a function f, right? And the type of this function is one that takes a tick A cross tick B, gives back a tick C. And what we want to get out of this, right, is a function that takes these in order. So tick A, arrow, tick B, arrow, tick C. All right, we'll move this down a little as well. And so what is this function? How do we write this function? Right. So our input is a function f, and our output is going to have to be a function that takes these arguments one at a time. Right, if our output's a function, we write a lambda expression. So say this is a function that takes an A and returns a function that takes a B and returns f of A comma B. Right, and so this takes a function that's not curried, one that takes its arguments in a tuple, and returns the curried version where it takes its arguments one at a time. Right, so we look at the type, and it's what we expect. It matches what we gave as its type signature. Right, so we could think of our add curried function, or we would call it add pair, right, that takes an x comma y and gives us back x plus y. Right, so what if we curry add pair, right, we get the curried type, right, and so curry add pair of 1, we'll let this be increment, and so we want to curry add pair, so it takes its arguments one at a time. We then give it that resulting function the value 1, and we should have an increment function, which we in fact do. All right, we can go the other direction, let uncurry of a function be the uncurried version. So now our input type is tick A, arrow, tick B, tick C. So we take this curried function, and what we want to return then is a function that's a tick A star tick B, right, to tick C. Right, so now we return a function, right, that takes a pair and applies that pair, or applies the elements of that pair, or they are applied to, they're used by that function rather. All right, so what does this look like? All right, so uncurry has the appropriate type. All right, so we could ask what happens if we uncurry add. Well, sure enough, we get the curried version of this. Right, so uncurry add applied to 1 comma 2 does in fact give us 3. All right, so what we've seen here is a couple simple functions: flip, compose, curry, and uncurry. And so these are useful when we need to modify functions in terms of the order in which they take arguments, if we want to compose functions, or we want to curry or uncurry them. And it all depends on particular use cases where we find a need for a function of a particular type, but what we have lying around are functions that are almost correct. They almost do the job for us, but the types are quite right, or they're curried when we need uncurried functions. So there's just more examples of ways which we can sort of nimbly manipulate functions in a language like OCaml. All right, so we'll move on from our section here on higher order functions to a more general discussion on expressions, values, and evaluation, and that will be in the next video.